In this video, we shall see the differential amplifiers. So, in the introduction, so let us consider a signal source which is generating a AC signal. So, it is having two lines. So, these two wires are relatively close to each other. So, assume that this signal which is carrying the this wire which is carrying the signal is passed to a noisy environment, so which is having a noise. Will since it is since these two wires are close to each other, so this noise will going to couple to both the wires with the equal amount, as we can see now. So when this wire pass through a noisy environment, at the output we can assume that this signal what we have will be having a noise along with the signal. So this is what we have. The noise is equally affecting both the lines of a two-wire system. So assume that this is 1 dash. So I want to amplify this signal. So if I want to amplify this signal passing through a noisy environment, the signal along with the noise will be fed to the amplifier. So let us assume that I have an amplifier which is a single-ended amplifier. So single-ended amplifier means one of the end is grounded. So with respect to ground, we are applying the input voltage to port number 1. So we shall assume that this 1 is connected to 1 and 1 dash is connected to 1 dash. Since 1 dash is grounded, so we are applying this signal, which is the signal along with the noise, will be applied to amplifier 1. So this amplifier 1 is of a single-ended amplifier. So now when it is amplified and measured across RL, a load resistor, we can see the output is amplified. Along with that, we can see the noise is also get amplified. So here we have the signal plus the noise. Here it is the signal is also amplified. Along with we have the noise output is also get amplified. It is very evident that noise as well as the signals are amplified. So let us see what happens if I apply the same signal, that signal having some noise, to an amplifier of type 2. So in this second type of amplifiers, so we don't have a common ground here. Now the entire waveform, which is a noisy version, is applied to this amplifier. Now we shall see what happens to the output now. Can you see now the output is a pure sine wave which is amplifying only the signal, the noise is suppressed. So this is purely because the noise is common to both the signals what we have at 1 and 1 dash. So this amplifier is a different type of amplifier compared to amplifier 1. So this second amplifier, amplifier 2, will amplify only the difference of the signal that is available between 1 and 1 dash. So difference of the signal is only the signal is the violet signal is different, but you can see the noise is exactly the noise at this wire at 1 and 1 dash will be same. So since it's a common noise, so that will be get projected. Only the signal which is not same, so will be get amplified. So as you can see here, only signal is amplified, the noise is suppressed. So this is an interesting thing. Now we need to develop an amplifier which will actually amplify the difference between the two signals. It is not an amplifier what we learned in the previous places where one of the input is grounded, like all CS, CG, CD amplifiers we have seen. All the amplifiers have one of their input grounded. So this is a single-ended amplifier. This is a differential amplifier where the input is applied between 1 and 1 dash. And one more observation, we'll have a look at this thing. So can you remember, this is the frequency response of a CS amplifier. We know that at low frequencies the gain is less, at mid frequency it is almost constant, at higher frequencies the gain reduced. Now we know that the cutoff frequency, which is at low frequency, is majorly due to the coupling capacitor. Now this is putting a limitation on the usage of that amplifier. It cannot amplify low frequency signal. So we need to have an amplifier which can amplify even the DC signal. So this can be made possible only if I don't have a coupling capacitor. So the amplifier should have no coupling capacitor, so that this F1, which was due to coupling capacitor, can be totally eliminated, so that the signal, the amplifier can amplify even the smallest of frequency signal, including the DC. So these are two requirements to suppress the noise and to have the DC gain. So we go for a differential amplifier. Now we shall see a differential amplifier in two different modes. One is common mode. So we shall first analyze the large signal analysis of differential amplifier. So this is the circuit diagram of a differential amplifier. As you can see, we have MOSFET M1, M2 and two resistors as load, that is RD and RD. So we are assuming that both the resistors are same. And we can see at the tail we have a current source I, which is made to flow through the circuit, and there are two inputs which is written as V in 1 and V in 2. So these are the two inputs we are talking about in the previous amplifier 2. So it has a differential input. So one input is given here, the other input is given here. The output is VD1 and VD2, and we're going to have a current of ID1 flowing through M1 and ID2 flowing through M2. And we shall see what happens if it is grounded. Now you can see this is grounded here, this is grounded, and it's the same circuit. Input 1 and input 2 are grounded. When the two inputs are grounded, so here we can see that there is a VGS1 between M1, between the gate and source of M1, between gate and source of M2 we have VGS2. You can clearly see in the previous amplifiers of your CSCG, we used to have resistors to provide the biasing. Now since this minus VSS is there, and this minus VSS is sufficient to provide the required VGS for this one, and this current source will make sure that the required VGS is developed across the gate and source of both the transistors, so that it allows a current of required current. Now when these two gates are grounded, so the current flowing through both the transistor will be half of the tail current. I can see it is I by 2 and I by 2. So we're going to have a VD1 at the drain of M1 and VD2 at the drain of M2. Let us take an example and try to find out what is the different parameters. Now we shall assume a MOSFET with UNC of 200 microampere per volt square and a threshold voltage of 400 millivolts. We shall assume a W of 200. If we assume a tail current of 1 milliampere, the current flowing through M1 and M2 will be half of that, that is 500 microampere. We can actually find out what is the value of VGS that is required, that will be developed across each of the transistors using the expression for ID in saturation current, in saturation region. So VGS can be obtained as VTO plus under root of 2ID Kp into WL. So using these parameters, we'll get the VGS across both the MOSFETs developed will be 0.558 volts, that is 558 millivolts. With VDS as 0.9 and minus VS is also 0.9, with value of RD as 500 ohms. The VD1, the voltage at drain of M1 will be given by VDD minus the drop across this resistor, which will be equal to VD minus ID1 into RD, which comes out to be 650 millivolts. So we shall actually do a simulation of the same circuit and try to verify whether all these values are correct or not. This is circuit what we are looking at in the previous example. As you can see now, this is the MOSFET which we consider M1, M2 having a resistor of 500 ohm and a Kp and mu NC of Kp which is nothing but mu NC of 200 microampere per volt square. So we shall have a look at the same thing over here. This is what is Kp we have, and we are assuming current of 1 milliampere as a tail current, and this WL is 200 and WL of this is also 200 here, as you can see now. Is also 200. So let us simply do the DC operating condition and try to verify whether the currents flowing through M1 and M2 is equal to 500 microampere, and the voltage at the drain, that is VD1 and VD2, should be 0.65 volts. So let us see what is the values. Of course, Vs is the voltage at the source coupling point. VSS is minus 0.9. and the VGD is 0.9, and we have the output voltage. Since all these are DC voltages, since we are considering the large signal analysis, the voltage at V01 is 650 millivolts, so that's what desired, and of course which is the same at the second drain also, and we have a tail current of 1 milliampere. You can see the current flowing through M1 and M2, that is drain of M2 is 500 microampere, this is also 500 microampere, meaning that as long as the MOSFETs are there in saturation, the current flowing through both the MOSFETs is half of the current tail current. This way we can see that even without having a biasing resistor, the MOSFET is conducting because we have a minus 0.9 and plus 0.9. Even though this is grounded, 0 minus 0.9 over here is going to create a required voltage. You can also verify how much is the voltage at Vs here. So since, as you can see now, Vs is minus 0.558, the VGS of this is actually 0.558. So that's what is being verified in the previous slide also. As you can see now, the VGS is 0.558. So that's what is being clearly verified here. So this Vs corresponds to the voltage at this point, which is minus 0.558. So VGS happens to be plus 558 millivolts. So this way we can verify the current flowing through the MOSFETs are half of the tail current. We shall continue with the analysis of the large signal. Now what we do is we'll actually make this voltages common for the gate. As you can see now, this gate and this gate both are shorted. Now we shall apply a voltage over here and try to find out what is the maximum voltage that we can apply so that these MOSFETs are still in saturation region. So for that we are shorting both the gates and we are trying to apply a DC voltage and try to vary this, and let us see how does the analysis goes like. Now this is what we are actually looking at. What is VCM stands for the common mode signal. So what is the maximum common mode voltage that is allowed for this particular circuit so that M1, M2 are in saturation. So that means, so we are trying to find what is the common mode voltage to keep M1 and M2 in saturation. So we are actually, okay, how do we make out whether the MOSFET is saturation or not? So we'll actually estimate what is VDS. So what is VDS of this and VDS of this? If VDS of this is greater than or equal to VDS sat, we say that MOSFET is in saturation. So for VCM to be maximum, so VDS1 is equal to VDS2 should be equal to VOV. And as we know that VDS1 is nothing but VD1 minus VS1. That is potential across the drain and source is nothing but VDS. But what is VD1? The voltage at this drain 1 is nothing but VD minus ID1 into RD. So since we know that ID1 is equal to I by 2, we are writing VD1 is equal to VD minus I by 2 into RD. And if you actually write the KVL for this, so this is VCM, you have a VGS here and you have a VS here. So by writing the KVL here, you can write VCM, that is common mode voltage is given by VGS plus VS. So that's what is this expression. So that we can get what is the expression for Vs, because I need to know what is Vs in order to find VDS of M1. So Vs can be written as VCM minus of VGS. So that's what I'm writing here. So VCM will be equal to VCM max, so minus of VGS. So what is VS1 is nothing but Vs, and VOV can be written as VGS minus VTH. So what we'll do now is, so this VDS1 what we have here, this VDS1 is nothing but VD1. VD1 is actually given by VD minus I by 2 into RD. So that's what is written. This is actually VD1 minus of, this is actually VS1. So this VS1 is given by VCM minus VGS. So this is what is VCM max minus of VGS. So this VDS should be equal to VO. So that's what I'm writing here. So the maximum voltage is possible only when this is still in saturation. To keep it in saturation, we should be VOV. So upon solving this, we'll get the expression for VCM max as VD minus I by 2 RD plus VTH. So from